We've seen previously that if we start with a general power series and we differentiate this repeatedly, we're going to end up with some constant term in the expression. And by evaluating that series at the center C, we're going to end up with zero factors, which then allow us to isolate the different constant terms. So for example, if we start with the original f of x power series, we can substitute x equals c into this expression, and what ends up happening is all these factors here, all these factors end up being zero terms, and we're just going to be left with the original a0 coefficient. So if we do this for the derivative, so once we differentiate that expression, we're going to end up with an a1 coefficient, or an a1 constant term, and all the other terms are going to have an x minus c factor involved. So if we evaluate that at c, all those terms are going to cancel out, and we're just going to be left with an a1 term. If we differentiate that f prime again to the second derivative, we're going to end up again with another constant term. In this case, we have that extra factor of times 2 from the original x squared up here. But again, we're going to generate all these factors here, which when we plug in x equals c, are all going to end up becoming 0. And we end up being able to see what the a2 term is going to look like. And we then generalize the fact that if we evaluate those derivatives at c, and if we're going to evaluate those derivatives at c, we can generalize an expression for the a term. So this is where the theorem comes in. So theorem 1 states that if we take the nth derivative and divide it by n factorial, because that's going to be the pattern of those coefficients that are going to end up in front of the a term, if we divide by that n factorial, we're going to get the coefficient for an. And then we can generalize our Taylor series as a function by saying that, well, we can take the an part of that is going to be generated by this expression for every term. It's going to be the nth derivative evaluated at c divided by n factorial, and then we can apply the power series part of that, or multiply the power series part of that centered at c. And so we're going to get this expansion. At 0, we're going to just have the f of c evaluated at the center c. Here we have the next term. That's the degree 1 is going to use the first derivative. The degree 2 is going to use the second derivative. Degree 3, the third derivative, and so on and so on. And we can do this infinitely because this is an infinite series.